Hi, my name is Nicolas Cambier. So today I'm going to talk about this Emergent naming system that we created for unstructured environments, for localization specifically, and we apply this to a shortest path discovery. So this is the case study that I will talk about. So the context is that localization is essential for most robotic applications. So you have robots, you want to deploy them somewhere. That's because you want them to pick up something or to go somewhere or to achieve some task at some place. And maybe they need to communicate with each other and to agree on a place to meet. So it's really essential. But the issue is that if you go to in a cave or on exoplanets, for example, you don't have access to global navigation. Or at least it's really inaccurate if you are like in a forest that is with a lot of trees, a lot of covers. So you could also use odometry. So that means you tell your wheels to go at some speed for some time. And after that time, you know that you should have gone 5 meters forward. But again, if you are in these kinds of environments, you can't really be sure that it will work because, maybe the ground is not really stable. So you will have moved a little bit and it's really noisy. So you can't make good estimates. And so if you go outside of this kind of traditional robotics, in swarm robotics, we have actually a lot of alternatives to this kind of positioning. But the issue is that a lot of the time, the navigation is highly stochastic because you don't need the position. So you can explore the environment, but it's pretty random. And then when you want to go somewhere, you'll know how to go there. So just explore the environment randomly, and hopefully at some point you will find this place. So it works, but it takes a lot of time. So for time-critical missions, it's really not the best. And also, in addition to that, sometimes you want your swarm to make a decision about where to go or how to go there. But if you don't have the positions, how does the swarm communicate about that? So usually it requires a level of information that's quite that's not really reasonable to expect in these kinds of environments. So, for example, you need to know how many targets you have so that you can give them names beforehand, and then the robots can use those names to communicate to say, oh, I want to go to this target, or this target has a good quality that we should exploit. And so there are also other alternatives, but then you need a really high robot density. So we have this example here. You can see my, okay. So here in the bottom right, you have this example of robots that creates these chains to go from one place to the other. But that means that you need as many robots as it needs to create the whole chain. And then a lot of them can't move because they just have to stay there as beacons. So the question is, can we create a swarm robotics approach to localization without relying on any global positioning, without prior information, and working with as few robots as we can, and while still staying a swarm? So obviously, when you think about swarms and localization, you think about stigmergy, so like the pheromones that ants use to be able to move in the environment. But if you try to think about how you would do that with a robot to have the pheromones, it's really not obvious. So you have a lot of works like the one in the bottom here, where they use the LED screens, for example. So the robots are tracked and there is a projection on the screen of where they went so that other robots can follow that. You can also use some kind of alcohol-based solutions or other kind of really specific equipment. But again, if you are in a real environment, you can't really use these kind of tricks. So instead, we thought that we could take advantage from the fact that we are in an unstructured environment. And because an unstructured environment has a lot of salient points, right? You can see a lot of things from the ground, rocks, trees, stuff like that. So these are all kind of landmarks, and we can use those landmarks as beacons in the environment to talk about where we are and where we want to go. So the case study that we have here is a shortest path discovery. So we have this environment on the top right, and on the left of this environment, you have a nest where the robot starts, and on the bottom here, but it can be random, you have a source where they have to find something that is really interesting for them and to bring that back to the nest. So that's the first part. And now they have these landmarks that they use to repair each other, but they, again, cannot mark the environment. They can't mark the landmark. So instead, they remember in their own brains where they went. And so they deposit virtual pheromones into their memory that correspond to these landmarks. But again, the issue is that if they want to communicate about that to create this global pheromone that you would have in a swarm, they can't because they don't have names to say, oh, I was there last time, so this is the place that you should add pheromones to that. That doesn't work. Okay, so this is a robotics work. We did that in a realistic simulation with epochs. But here I'm going to only talk about the high level because for the sake of time. So there are a lot of things that you have to fiddle with to make that work on the low level, and it's all in the paper, but here we're going to stay above all of that. So it's kind of a classical example of stigmergic navigation. So I'm not going to be too long with that. So you have the ants, so that's a robot that starts at some point. So that's the nest in red. And it uses, so it can discover some landmarks that are around it, that are not too far. And it gives a value of tau 0.1 to these landmarks. And also, because it's already in the nest, it will add a value also of, well, actually not tau zeta, but it's the same value 0.1 to the place where it is. And it moves to one of those things randomly. So the probability of moving to the next landmark is weighted by the pheromones that they have. And it goes to that place. And it also puts zeta more into that place. And the rest evaporates at the rate rho. And you can also see that the nest now is surrounded by red. So it's kind of on the blacklist where it just, the robot will avoid going back there unless it really has no other alternative. So, and then again, it creates new landmarks here on the right and on the bottom. And again, it gives it a value of 0.1. So you can see here that already it has a higher probability of going to the right or to the bottom than going up or to the left. So it goes to the bottom. Here we are lucky it found the source. And now you can see that the middle landmark is also on the blacklist. But because it found the source, it will just forget the blacklist. So now it can't go back and use any of those nodes. So it will just go this way this time, and eventually it will find the nest. So you can see here that we have kind of on the top that is not on any path to go to the source. The value of the pheromone is quite low, so it will have a lower probability of going there. But it can use either the path on the right or on the bottom to go to the source. But obviously, if you have only one robot doing that, you're not really sure that it's going to work because it will basically use the path that it has already found and use it again and again and again because the probability is higher there, and this probability will become higher and higher. So it has found a path, but not the shortest path. So the shortest path, you can only find it by cooperating with other robots. So this is kind of a low watermark that we use for this work. So how much they can, what is the path that they can find by not communicating and having a fully individual behavior. And the high watermark is the opposite. So in this case, we assume that they indeed knew about the landmarks before and they have names for that, and they can communicate about them. But how do they communicate? So it's kind of a cooperative exploration. And so at any point in time when they find a landmark, they have a probability of sending a message to other robots surrounding them. And this probability also evaporates like the pheromones, according to the time since it last went to the nest or to the source. So if you just found the source and then you find a landmark, you have a high probability of saying, oh, I was at the source just now and now I'm here. But if it was 5 minutes ago and you have not found the source of the landmarks, then maybe that means that you are kind of lost and you maybe shouldn't talk. So the probability is much lower to talk. But then, okay, so you talk. And what do you say? You give the names of so where you are, and the place where you were before. So where you are, obviously, it's quite important because then if you have a lot of robots that are in the same place and you receive all of the messages, and again, this has a high probability of saying these messages, that means that you are quite close from the nest or the source. So that's good. So you increase also by zeta, so the same value as you were using to increase the landmarks when you get there. But you don't need names for that because that is the place where you are. Where it's really interesting to have names is when you talk about the past. So in addition to saying, I'm here, you also say, I was there before, I'm coming from there, and this was also quite close to where we want to go. So with names, that's cool, but without names, how do you do that? What we use is the minimal naming game. So it's one of the many language games which are a model that was developed to study the self-recognition of language in humans. And the minimal naming game is the most simplified version of all of those. And the concept is really simple. So we have two robots that meet, and these robots have a lexicon. So it's a list of words that correspond to the topic that they are talking about. So in this case, they meet at the landmark. So they have a lexicon that corresponds to this landmark specifically. And this lexicon is a list of words. So one of the robots will decide to speak, will communicate, and it will select one of the random words in this lexicon. If the lexicon is empty, so it has maybe never met this landmark before, so the lexicon is empty, it will create a random word. But in this case, okay, it already has one, so it communicates. And then the other robot checks in its own lexicon if there is already this word. So in the case on the left, it doesn't have that, so it adds the word to its own lexicon. So that's a game failure because the second robot has to learn, and they don't really agree. And on the other case, maybe the robot will choose the word A, and then the second robot will actually know that word, so it will reduce its lexicon to the word A. So you can see that eventually they can converge. If they know the same words, they can converge and use only one name to give to this landmark. So that's cool, but that's only useful if we know what we are talking about. So when you want to say something about where you are right now, we know this is the current place, so we do the naming game on that place. But what do you do when you receive two words? So the robot that sends a message is also talking about where it's coming from. You don't know where it's coming from. That's the whole point. So how do you find out what it's talking about? Then you look at all your landmarks that you know, and you look in all these lexicons if you find that word that the robot said. If you have only one of those landmarks, that means that it's talking about this one, and you can improve it. But if it has many of those, then you will select one randomly, and then you will play the naming game with that. So hopefully the lexicon for this landmark will reduce to one word, and then you will forget the word for all other landmarks. So you will also, you see that this landmark will also converge to that single word. So that's the point. In the end, we want all the landmarks to have only one word that all the robots know. Okay, so a little demonstration. So here we have, so it's the same environment in all cases. The robots start in their nests, and they want to go to the target that is more or less in the middle. So on the left, we have no communication. So robots won't communicate at all. It's purely individual. On the right, we have prior. So that means that they have prior names. So when they discover a landmark, they all use the same name to talk about it. So it's a low watermark on the left, high watermark on prior on the right. And in the middle, that's where they try to agree on an actual name. So let's see how it goes. Oh yeah, and you can see that there are circles around the landmark. In all cases, apart from no communication. So these circles represent different words. So they have colors and size that represent different kinds of words. So you can see that in prior cases, there's only one circle, so one word per landmark, because they all know this name. But in the case of the minimal guessing game, they have to agree. So sometimes there are more than one circle per landmark. And I think it's quite clear already that you can see that with no communication, they are kind of doing something random, and they even lost the nest a little bit. Whereas with the minimal guessing game and prior, they are starting to find some paths, and even maybe the shortest path is starting to be clearer and clearer. And, I don't know if you can see it here, but when they find the source, they kind of get a cylinder on top of them. That is the item that they have to retrieve. Yeah, so now you can already quite clearly see that the path that goes from really completely horizontal from the left to the right is starting to really emerge in prior, and even in minimal guessing game, you can start to see it. So that's a demonstration, that's cool, but now the question is how can we quantify that, because we didn't even see the pheromones there. So what does it look like? So we plotted, so we did 50 runs for each of these 3 cases with also only one message, so only talking about the present or talking about both the present and the past. And we did that with 10 robots and 50 robots. And then we binned all the landmarks that were in those 50 different runs. So that's 50 different environments with different landmarks. And we plotted these landmarks according to the distance from the nest horizontally and the source vertically. And we give the pheromones as colors. So if they are on the diagonal that goes from 6 to 6, that means that they are on the direct line that goes between the nest and the source. And if they are somewhere above that, that means that they're not on the optimal path. And you can quite clearly see that on this direct line, there are much more pheromones that are deposited. So it's quite encouraging. But still, you can also see that if you have a message size of 1, then you have some issues because the path is a little bit more fuzzy. But there is still a path that kind of emerges. So in terms of lap time, so that means the time that it takes to go from the source to the nest. We can see that it reduces as the size of the message increase. So if you have no communication at all, by the way, if you have no communication at all, it's the same if you use prior or the minimal guessing game because you don't communicate anyway. So it's quite high because they don't find the optimal path, they just find a path. But then as soon as you start talking, then it reduces considerably. But still, if you are able to talk about the past also, it reduces even more. And what's really interesting is that you can see that the difference between knowing the names before or agreeing on the names during the experiments is almost insignificant. So you can say that there is really almost no difference, and the lap time increases whether you know the name or whether you create the name as the experiment goes. And also, so we show that the pheromones, when you have only 10 robots, are so we have less pheromones, but it doesn't apparently impact the quality of the lap time. So even if the pheromone path is fuzzier, you can still find actually path, and you can still find the shortest path. But now you can look at the vocabulary too. So that's really the part that is maybe one of the most interesting. So here we have different lines, and we have the name that is given to the nest. So that's only for the minimal guessing game. You have the name that is given to the nest in blue, the name that is given to the source in orange, and all the landmarks that are on the shortest path are averaged on the green line, and then all of the landmarks that are kind of irrelevant because they're not on the shortest path, you don't want to have them, is on red. And then on purple with the little dashes, you have the overlap. So that means the number of words that are actually in multiple landmarks at the same time. So these are homonyms in effect. And if you look at it, you can see that there is kind of an explosion of names for the source initially. And that's because the robots find the source at different times, and then they leave. So it takes a while for them to converge to a name. So initially, they all create different names, but they all eventually converge to the same thing. And then it's the same for the nest and for the shortest path. They find the right name. Yes, and there is some overlap also, but for the other landmarks, then you can really see that it basically explodes and they never converge. So because the other landmarks are irrelevant in a way, they don't find a reason to converge. So I think that's really interesting what we found here, because in effect, the robots are able to map a path from the nest to the source. But, sorry. So yeah, so they find the path from the nest to the source, but they didn't need to map the environments. They just have to have their own landmarks and to have the pheromones in their brains. And they don't even remember the path from one pheromone to the next. They just remember, oh, I see these landmarks and I should go there. So they didn't create any topological map. And actually, that's quite similar to how humans and animals create a representation of space. So here there is a link between the representations of space and the language that they create as they create it. And then also what's really interesting is that, so as we saw, there is some homonyms here and some synonyms. So that means that they don't have to convert those more sometimes. Sometimes they can just have some words that mean a lot of things or different things. But it doesn't seem to affect the eventual quality of the solution. So why does that happen? So we have this hypothesis that maybe they create words that mean some categories. So they can have a word that maybe means all the landmarks that are not relevant. So at some point, it doesn't really matter that this word corresponds to multiple landmarks or just one, because it's not relevant. So they have this kind of emergent categories of meaning that are quite interesting. Yeah. Okay, then so in conclusion, we create this new threading approach that uses certain features in the environment to build a virtual pheromone trail. And the robots use direct communication instead of stigmergy. And what's really interesting for me is that this is the first ever implementation of an actual robotic culture that is flexible to uncertain variations, that is useful for the task at hand, that is not assuming a shared sensory space or detection model, and perhaps, but we have to see, is enabling emergent meaning. So for me, this is the first step towards robots that are truly independent, because they are able to name the situation, so they could eventually tackle unexpected situations by creating names and talking about them. So in future work, we want to apply this to a lot of other applications. So instead of short espace discovery, we can have area monitoring by just avoiding high pheromones instead of going to them. And that's been done already, but without the naming game and talking about the past, just talking about where we are right now. And also we could tackle the actual landmarks discrimination, because right now we assume that they are able to recognize different landmarks by themselves, but we could also use a different variation of the language games that is called the category game, and that enables them to just create also the category, so create the difference in the symbols as well as the meaning as they are talking, and try to create this emerging vocabulary. And then eventually, to really know if we have this emergent naming that appeared, we would like to analyze the emerged vocabulary. Okay, thank you very much. And I will now respond to questions.